Hello, myself Dr. Runu Banerjee, professor from the Department of Instrumentation and Electronics Engineering, Jadavpur University, Kolkata. Our research area is on electronic olfaction and taste sensing. This is purely an interdisciplinary subject which starts from the material exploration for sensor preparation to the decision making exploring artificial intelligence. Here I will try to brief our research objective and how we are proceeding towards the objective. As we all know that human perception can be utilized using machine perception by several instruments like vision using camera, audio system using microphone. Our research area focuses on smell and taste sensing system that is called by the machine system is called electronic nose and electronic tongue respectively. Now, why machine perception for this sensing system is required? Say this is an example for tea quality detection. For tea quality, there are major attributes based on color, taste, aroma, strain. Among these, taste parameters are responsible for non-volatile molecules and aroma is due to the volatile molecules present within the tea mixture. Now, worldwide accepted practice is using sensory panel. They used to provide score by human perception on taste, aroma, taste, and astringency like that in a scale of 1 to 10. But this is purely subjective and non-repeatable. Now, how this odor sensing system for human perception works, that depends on, as we know, the stimulated systems are called olfactory epithelium cells present in the roof of nasal cavity. And human can recognize up to 10,000 different substances based on their odor quality. This is the human olfaction system physiology, that we perceive the aroma through nose and the olfactory cells activates, then sends the signal to the brain, and brain using the pattern recognition system, that is, we can distinguish the odor quality using a high-end pattern recognition system present in our brain. The instrumental system, that is the electronic nose system, is basically an attempt to mimic this human perception system, though the human olfactory system is quite complex, and that's why it can detect up to 10,000 different odors. Now, this is the why it is needed, because the human systems are subjective and vary person to person. It depends on mental conditions, physical and mental conditions. So, an repetitive object-oriented system is required for machine perception. That is called electronic nose. Besides these sensory systems, there are certain high-end instruments like gas chromatogram, mass spectrometry, and other high-end systems based on gas chromatography system. Those are very specific for declaring the constituent present in a complex mixture. The quantitative amount can be known using this instrument. But these are time-consuming, laborious, and expert operator required for system operation, and purely laboratory-based systems, not the field trial is feasible with these high-end instruments. And of course, the systems are costly. So electronic nose is a machine that is used to detect the complex odors using sensor array. The sensor array consists of number of sensors. Those may be non-specific or specific. In our first generation system, electronic nose, we used non-specific sensor array. I will coming to the specific sensors also. Now, these odors, when the sensor exposed to the gas, the odor stimulus generates a characteristic fingerprint from the sensor array, and that should be classified using a suitable pattern recognition engine to declare the odor quality. This electronic nose has wide application for environmental monitoring in the area of medical diagnosis and healthcare systems, food and beverage quality analysis, automotive and aerospace application, cosmetic systems, explosive detection. Our research area confined within the food beverage applications, and presently we are trying to extend our work on medical diagnosis also. The basic components for an electronic nose system requires our odor delivery system, then the sensor array, then the signal conditioning and data acquisition. This portion is the instrumentation, the signal conditioning, data acquisition, and signal processing. Then, using a suitable pattern recognition engine, the quality of a particular odor can be declared. So it consists of three major units. One is sample delivery system that enables the the gas generation to the sensor chamber. Then the detection system, that is the sensor development part, and the computing system, that is the from the electrical response, the quality of odor can be identified using a computing system that explores the artificial intelligence. These are the different type of sensor normally used for gas sensing: metal oxide semiconductor sensor, conducting polymer sensor, quartz crystal microbalance system sensor. In our first generation electronic nose, we used MOS sensors. These are TGS MOS sensors procured from market. These are standard MOS sensors, non-specific sensors. This 5 sensor array was developed for gas sensing. This is the sample holding system. This is the complete set for electronic nose, and this display shows the electrical parameter change. For MOS sensor, the resistance changes when it exposed to the gas. From this electrical parameter change, the odor quality should be declared. For performance of a gas sensor, the required features are: the sensors must have high sensitivity, high selectivity, small response time, good reversibility, low fabrication cost, and of course the low energy consumption. For most sensors, these are very stable sensors, but the operating temperature required 300 to 500 degrees centigrade. Most sensors are easily available in market, but these are non-specific sensors. In our second generation, we are working presently using quartz crystal sensor. It has a wide number of features for using quartz crystal sensor. The principle of operating is when the gas exposed on the sensor surface, then the mass changes, and accordingly, this is piezoelectric principle, that mass change reflects as a frequency change. Then the frequency change parameter should be converted using suitable signal conditioning system to the for odor quality detection. It has number of features like low cost, high sensitivity, fabrication easiness, and all these features supports this QCM as a new optimal choice for gas sensing. We normally use to coat the surface using a polymer material. That should be the another part, that is the material exploration. Wide range of chemistry application is there for material preparation. Then the surface should be coated with a polymer material. When it is exposed to the gas mixture, then the it absorbs the polymer material absorbs the gas molecules. Accordingly, mass change and the frequency will change will reflect the presence of gas molecules within the complex odor gas sample. Then this should be purged to release the adsorbed molecule from the surface for reusing. This is the procedure of using QCM sensor. As I told that this is an attempt to mimic the human sensory systems to the machine sensor system using QCM sensor. Now coming to the specific sensor development using molecular imprinted polymer technology. The beauty of this molecular imprinting technique is we use the template as the target molecule. That is, if the sensor should be designed for a particular molecule, say for geraniol, then this template should be the geraniol. This geraniol is polymerized with certain monomer and crosslinker. Then with the initiator, then it forms the polymer. After polymerization, this template should be removed by washing it with suitable reagent so that a vacant site can be created for that typical molecule. Say for geraniol, if we expose now the sensor material formed as the cavity for geraniol. If this material is used for the sensor preparation and then the sensor when exposed to the gas complex gas mixture, if it presents with the geraniol, then that will be easily attracted within the cavity and it is highly sensitive. So it will increase the sensitivity for a typical or the specific molecule. So this is the procedure for using MIP. This is an example of using MIP QCM sensor for hydrocarbon detection. This application is not for the food quality area, rather for health area. Because these aromatic hydrocarbons are highly hazardous for health issues. And the sensor development was very difficult as these aromatic hydrocarbons are highly volatile and it is difficult to use as template. So we used a dummy template which is more or less similar structure but poorly volatile. These are the issues with these aromatic hydrocarbons for which causes health hazard. Now this is the material exploration part. How these are the 10 different templates had been tried, attempted for sensor development. These are different binder variations because the after polymerization, the material is a powdered form, then it is binded with certain oil. So it requires a rigorous optimization technique for each. Say for monomer, for crosslinker, then for solvents, then for the binders. A wide range of optimization confirms the polymer for particular material preparation. After preparation of the sensor material, it will be coated within the crystal surface, and this should be placed within the sensor chamber and exposed with the gas. Accordingly, the response will be noted by this portion is the device part, how the signal will be processed, and this is the pattern generation or odor quality detection system. Now the material whatever the material is prepared, that should be confirmed using certain material characterizations using Fourier transform infrared systems, FTIR, using scanning electron microscope, using AFM. So these are the material characterization part, and these are the frequency responses for different concentration range, as well as with the exposure of different hydrocarbons for all the sensors. So it requires a rigorous experimentation. And finally, this is the real-time response for MIP QCM sensor for this typical template used as the dummy template for benzene detection. Here you can see that for benzene, that frequency deviation is maximum than from other hydrocarbons. This is the drop casting technique for sensor preparation, and this is the experimental setup. For this experimental setup is also developed by our team. That means the device part, where a crystal oscillator, CMOS crystal oscillator, is followed by a microcontroller. This is the device layout developed by our team, and this is the portable handheld system, where this portion is the sensor chamber, and this is the device, that is the controller and the oscillator portion. From the frequency deviation, we can declare the quality of typical molecule present within a gas mixture. This device has already been patented with the patent number this. So we can summarize this electronic nose area for our work, that the MIP based QCM sensors exhibited good sensitivity, high selectivity, significantly lower detection limit, and good repeatability, reproducibility, as well as high durability. That means it can work without loss of sensitivity for up to 3 months. Since these are extremely low cost solution, so this 3-month usage is quite satisfactory. We have so far 15 journal publications and 8+ conferences in this area, and present ongoing project is supported from ACRB Sure India, ANRF, for 3 years. It will continue up to 26 October. So this is the MIP QCM area, and we are presently working. This project is for spice quality detection. So we are working in the food area. Another component of our work is electronic taste detection. As we know that electronic taste, the work area is more or less same. Only difference is the quality detected in terms of aroma for electronic nose, and for tongue this is based on taste features, because food quality should be detected, that is the nutrition, health, and of course the adulterant use hazards human health, and this quality should be detected using electronic test systems. So for protecting public health, maintaining food quality, addressing consumer demand, overcoming analytical gap, these are the reason for approaching towards this area. And the electronic tongue system is structurally similar to electronic nose systems, as the difference is the operating sample in liquid state and the sensor array at the electrochemical sensor array. Then again, signal conditioning and data acquisition system, then pattern recognition system is required. In our setup, we use voltammetric methods for as a 3 electrode system, so working electrode, reference electrode, and counter electrode, the standard electrochemistry. And this is the attempt of preparing an electronic tongue where a number of working electrodes are there, along with counter electrode and one reference electrode, and this voltammetric signal which will be generated, then that should be sent to the pattern recognition system for the test quality detection. Again, this is our first generation electronic tongue using non-specific sensor array using noble metal arrays. And this is the setup which we used earlier. This was also developed in our lab for non-specific sensor array using metal electrodes. Now, coming to the specific type sensor, this is one example of detection of thiaflavin in tea. Thiaflavin has several beneficial usage, health impact, the health benefits, the antibacterial, anti-allergic, and it is present in sufficient amount in tea. This is again the sensor preparation procedure which we used for electronic nose or MIP QCM system. This is for MIP electrochemical system. The material should be, after polymerization, the material should be dried and crushed within a mortar pestle system. Then used a binder as a paraffin oil. Then it should be inserted within the glass electrode. It will look like this, a very simple glass electrode, and we used for this as the working electrode for voltammetric measurement system. Again, this material characterization, just like the MIP QCM system, so that for confirmation of the MIP formation, this FTIR spectroscopy, again the same images are required. Wide range of experimentation required for confirmation of typical sensor formation, and these are the buffer selection, pH selection, selectivity of this shows the selectivity, that is the sensor material is highly selective for TF, and these are the close structure to the TF and present within the T samples, but the sensitivity is quite weak. So the sensor is typically developed for MIP sensor, TF, that is thiaflavin detection, and it is highly selective for this thiaflavin. This is the real sample analysis for black tea. The black tea sample is sent through the census system, or the after collection, the data analysis should be done using certain pattern recognition system, that is the using a PLSR based model for regression. This is the actual value. Actual value is obtained from the HPLC, which is again the high-end instrument and precise, much more precise. And we can see that this is the predicted TF that is detected from the census system, and the accuracy is almost 99%. So this is the output of the system, and this is the system is developed by using a certain regression model, PLSR. This work has been published. This is actually our first MIP electrochemical work. This work published in Sensor Actuator B, chemical of Elsevier. And this is, as per literature review, this is the first MIP sensor for quantitative TF detection. The difference of non-specific sensor and specific sensor usage is, for specific sensor, the quantitative presence of a particular target material, target component within a complex mixture can be defined using this specific sensor, sensing technology MIP. And using non-specific sensor, the qualitative discrimination is possible, but this quantitative detection is not feasible, rather hardly feasible, because it is not particularly designed for that particular for a particular target. This work has been patented with this patent number. This is for black tea application, and the work has already been published. This work has been extended for several agro and food quality detection, food nutrient detection, adulteration detection. We have around 40 plus SCI journals and 20 plus conferences in this area. Present ongoing project in this area is supported by CSIR Aspire for 3 years. This project will continue up to February 27. We have worked for developed for a device also, that is for a specific sensor array. This sensor that is this is for a tea quality detection. We have developed a 3 array sensor. This device has already been developed by our team, and this is the circuit, and this is the performance of the for individual sensor. These 3 sensors are for tannic acid, theaflavin, and theophylline, and for individual sensors the performance is like that. And after using the array, the overall performance increases from this 895 to 968. So actually the complex mixture consists of number of constituents, not the quality depends on single constituent. So we attempted to develop an electronic tongue with a specific sensor array. So far we have developed with 3 sensors array. This work has already been published in IEEE Sensor. So we are in a process to extend this work for a more number of sensors and for other application also. So the future scope, that is this is a very brief presentation for this whole work. So this work can be extended for different analyte detections, for comprehensive nutrient detections, and advanced machine learning systems can be explored. The sensor type, the glass electrode sensor, can be modified in a screen printed electrodes and disposable paper based electrode. We are also in the process of developing the sensor shape and sensor durability, so that the more economically viable and deployable sensor can be developed. And the portable integrated device, because for electrochemical sense, for electronic nose system, for QCM system, we have developed our own system, which is already patented. But for electrochemical system, we have used so far, rather we are using high-end instrument that is made from Autolab for measurement purpose. Now we are attempting to develop the portable integrated device, so that the device is a low cost and must be integrated with MIP sensor, which must be handled for field trials. We are also in the process of developing that sensor. So this is the overall presentation of our research area in brief. So thank you.